So this is the third example of NGon examples. Okay, the first one, we start from this mesh. Okay, this mesh, you know how to create this mesh, right? We start from a curved surface, and then we subdivide it into hexagonal patterns. We adjust some of these parameters, we get these convex hexagons, okay, as a mesh. And then we start from here, we can try to do some transformation. Okay, first component introduces from here is called extrude edges. So we extrude all the edges for some certain distance following the normal direction or the normal vector of these curved surfaces. We can use this parameter to control the distance for extrusion. Okay, and then here, cap. You want to cap it or without. If without, then we have only these partitions that divide all the cells, all these hexagonal cells. Or we want to have a cap on it, then you get this. Okay, this M merge. Okay, if you turn it on, we can use a text panel to show what you get. You get one mesh. But if you turn it off, then you get a lot of meshes. Each of the mesh actually is this hexagonal shape. You can regard it as a cell. It depends on what you want to do. Sometimes you want to merge it, sometimes you don't want to merge it. Okay. And how about this one? If you turn it on, then it extrudes the structure on both sides of the surface. If you turn it on, off, then you extrude it only on one side. Okay. If the original mesh is on the top, if it is here, then it will extrude either within or without, outward or inward. Okay, but if you turn this true, then it will extrude it on both inward and outward. Okay, and if you use this NGon preview component, okay, now it is interesting because they are not merged. But if you merge them, here merge, okay, and you find it become like this. And remember, they are two-sided. Okay, so by default, the front surface is red, and the back surface is gray, and then black for the edges. Okay, so you can define colors for these three parameters and get this NGon preview. Okay, and you can bake it, so it will become a Rhino object. No? Why? Won't work? How come? Shouldn't be like that. Or let me bake this one. Okay, now it works. So we can bake it, it becomes a Rhino object. Okay, but somehow. Oh yeah, we did. Oh, no more? Okay, so I think we can bake it. No? Anyway, at least we can bake this component. Okay. Now this example, we have curves, another set of curves. Okay, and then we can loft it. Okay, It is strange. Okay, I am not quite sure why. Sometimes when you have NGon component, you are not able to show it unless you turn the preview on. Okay, usually no matter if it is, for example, like this curve, even if you turn the preview off, when you turn this green cylinder on, and if you highlight it, then you still can see it here, right? But for NGon component, if the preview is off, even if you have checked here this box with the green cylinder, and you select it, you still cannot see it, okay? And there are different ways to show it. One way is to use a Grasshopper component to connect to the output of it, and you can show it this way. Or you switch the preview on and select it, then you can see it. But when you don't select it, it disappears, even if the preview is on. Okay, and it will show it when you uncheck this one. Okay. But when you check it, then you don't see this unless you select it and then also turn the preview on. This is something quite strange to me, but anyway, I don't know why it is like that. Okay, so you can create loft object based on curves. Okay, and you can define the UV. Let me see. Okay, but how about a V? Okay, so for each individual curve, or actually for each surface, you get U and V, and then you can control the UV divisions. Okay, you get a mesh, and what is this? Distance, or I don't really know what is it. Maybe later we try some thing, we can figure it out. Okay. Curve loft. Okay, loft curves. For this example, we have two sets of curves. One is enclosed and the others are opened. And then we lock it. Okay. And what is this? Fast. Fast loft or slower loft. Anyway. We have curve, we merge them all together, but this is not. You see, they are grafted, okay? And then you loft them. Loft polylines. Okay. You graft them, and then you merge them, and then you loft it within C0 without to the C1, but you get the same thing. You get 5 meshes. You get 5 meshes. I think they are the same. Okay. Love to set cross polyline with holes. Let's check. Okay. So this is the boundary, and this is the hole. And we merge them together, then in Rhino it becomes an enclosed area with holes. Okay? And another shape, the boundary and also the holes, and they are on the same plane. They should be planar and on the same plane. And then you merge them together. If you check the tree structure, then you see that they are in the same branch. in the same branch, the boundary and the holes. Okay, but after you entwine them, they are separated in different branches for each of this one. This is in one branch and this is in another branch. This is very important. And then you loft them. Okay? See, this is one and this is another one. And this is one, the bottom side of it, another one, the bottom side of it, and then you loft the top one to the bottom, you loft the top one to the bottom. So eventually you create two solid objects with the loft operation. Okay, one mesh is the top one mesh is the bottom one, and then you preview them. Okay, we weld meshes. If you check here, vertex 204 faces 110. After you weld it, wow, you get more vertices. Why? Radius for welding. Okay, sorry, I'm not quite sure what happened by doing this. It has a radius for welding, and it increases number of vertices, but the faces are the same. Okay, I think somehow we have to figure it out if we need to use this. Okay. And an interesting thing, the radius is negative. Why is that? What happens if it is positive? You don't see any difference? Ha! I see. See the difference? You get the difference? No? Let me do it again. Okay, remember. Okay, the rendering. Make sure you remember it. Then I change it to positive. Are they the same? See the difference? The rendering, you have to look at the rendering. The shape is exactly the same, but the rendering. How about if I, in this way you don't see the difference. We have to see it this way. I do it again, okay? Now it is positive, and I make it negative. Maybe this time I'll try -1. What? What? Doesn't like it? What is the difference? The rendering. Yeah? Remember it? Okay, I'll do it again. +3. The shading, right? Why is that? Now I understand why the number of vertices become more after you weld the mesh. No, less, not more. Oh yeah. So when it is positive, then it is less vertex than when it is negative. See, now it becomes 364. Why is that? Let me see if I can do -2. -2, 364. How about -1? It doesn't make it. Okay, now I understand. How about -4? I guess it is the same. Still don't like it? Oh no. How about 5? Still. So it takes only -2 and 3. But how about +2? 68, the same. You see, the corners and the edges are blurred. Why is that? For mesh, the coloring of meshes are defined on vertices instead of surfaces. Okay? And it tries to shade the entire object based on the normal of the corner and the coloring of the corner. And you see, for the normal of this corner, actually it is the average of the 3 surfaces, the weighted average of the 3 surfaces. So somehow it is extruded toward us, and the corner is the other one. And then it tries to render the shade or the shading of all the pixels based on the relation between the pixel with all the corners that surround it. Okay, so in this case, you get gradient from here to here. Okay, if you take a look at one surface, actually physically the entire surface should be of the same shading, right? Because you assume the light source comes from one direction, and depending on the angle, the orientation of this surface, you should have constant shading for the entire surface. But somehow the rendering is strange because you get gradients. It's because for meshes, the coloring is based on the corners, the vertices, not on faces. Why is that? Because sometimes we want to simulate smooth object using meshes. So this is a very good strategy for computer graphics to do this. Okay, but if you have coloring on vertex, but somehow you still want to display the polygonal surfaces, what can you do? You regard the vertex of this top surface different from the vertex of the side surface. Even though they have the same coordinates, you still consider them as separated vertices. Okay? So you use this number, either it's negative or positive, to control which way you want it. And for showing this very clear boundary between two surfaces that are not oriented the same way, not a different orientation, then they need to duplicate the vertices, the shared vertices. So that's the reason why when you put negative value for this, then the number of vertices increases, because the corners, the shared vertex, for example, like this vertex is shared by 1, 2, 3, 3 surfaces. So this vertex is tripled. Okay, 364. Are all of them tripled? Maybe more than tripled, because here this vertex shared by 1, 2, 3, 4, 5, 6, 7, or even 8 or 9. I'm not quite sure, okay? But somehow it does change a lot. It's +2, it becomes 68, okay? Okay, NGon frames. We have a mesh like this. You divide it by, subdivide the original mesh, and then you create a frame. You have to set the preview on, then you get a frame. Why it is a frame? You see it? This is the mesh. This is the frame. So this distance, offset, decide the offset distance of each cell from the center, I think. Okay. So when it is large, it is approaching the edge of each of these polygon, and the frame becomes thinner. But when it is smaller, then it is approaching the center of it, so that the frame becomes wider. And what you get, polylines, you have to, okay, polylines, more mesh. Okay, it is a mesh, but you get it from this polyline. And how about this one? Okay, so if this is architecture, it is a structure, and then you have edges. Okay, you have boundary structure, and you have panels. This can be glasses, and this can be aluminum extrusions. Okay, and what are these? This is the outer boundary. Oh no, this is the inner panel. This is panel. Okay, you see, this is kind of V-shaped, right? Because they are not planar. But if you choose this one, then you have changed this V shape into this hexagon. I don't think they are planar. They are not planar, but somehow you can find this. And you need to clean the tree because some slot of it, they are empty. I think they are these missing edges. Okay, or you call them half edges, because they are at the boundary of the mesh, and this edge is only one-sided, which means this edge has only one side. Okay, it is empty along the other side, so these are the naked edges, and for these naked edges you don't get any of this shape here. Okay, but from here actually you get at least half of it. Okay. Okay, this is also very useful for architecture designer. NGon mesh offset by normal. Okay, let me